Okay, so today I want to finish talking about monads, and so there's two main ideas today. So the first one is trying to motivate where the monad definition is coming from again. And the second one, which we'll stumble into, is the power of having first order things you can look at. But let's start with where the monads come from. So last time we had this definition of a monad, which was a functor on some category C, which had a return and a join. And we were thinking of a returner saying, well, if you have 0 occurrences of M, then you can make 1 occurrence of M kind of vacuously. And the join is saying if you have 2 occurrences of M of X, then you can join that together into 1 occurrence of M, right? So that makes some kind of operational sense if you think of this as layers of M. There's a canonical way to do it. But then we saw there are many examples of monads. But when we saw these examples, we also had these different laws, which said that if you make a vacuous M starting in an M already and then join it together, then you get back to the identity. And if you do that, you can either do that on the inside or on the outside, right? This is outside, this is inside. And finally, there was one law that said that, well, if you have 3 M's, then there's 2 ways you can join them together into 1 M. And the law says that it's the same no matter how you do it, right? So these make some kind of intuitive sense. But we also saw that you can formulate other equations which don't quite make intuitive sense, right? Where if you start with 2 M's, you join it together and you blow it up again to 2 M's, then that's in some sense throwing away information. So that's probably not a law you want, but it's still a law you could consider, right? And it's not going to be true for many monads you care about, but maybe that's their problem. Maybe you shouldn't care about these monads. It's not completely clear where these laws are coming from, right? So today I'll try to motivate where they're coming from. And now, Colin, you can say what you think.
Yeah, well, the TLDR is that it will be extremely unsurprising. You know, the thing that you're used to right from the first time you ever wrote a program with semicolons in it, that that you don't have to group the semicolons you don't have extra bracketing to say which semicolon is more important than which other semicolon. But, you know, that semicolons are associative. You know, that's just normal, right?
Yeah. So what you mean is if you think of a Java program where each line has some kind of effect, then you don't have to bracket these effects, right? You're saying, well, I'm doing line 1, then line 2, then line 3. Don't have to say I do line and then I do 2 and 3, yes. or 1 and 2 and then 3, right?
Yeah. And likewise, you fully expect if you've got a command that does nothing, that, you know, often called skip, that adding extra skips doesn't, or taking them away, doesn't make the blindest difference to what your program does. You know, so that's so what's really going on is establishing that things behave the way normal programming constructions do, you know, in sequential code.
So, okay, so how do we actually make sense of that? So one way to make sense of that, so we're talking about composing things and bracketing things doesn't matter. And we're talking about doing nothing. So one way to make sense of that is to actually make a category where you have these effectful functions, right?
Yeah, because categories talk about ways of composing things and ways of doing nothing.
Yeah. So this is called the Kleisli category of a monad. The Kleisli was a Swiss mathematician who first invented this construction. So we're going to take a monad on some category C. So that's a functor from C to C with a return and a join that satisfies these laws. And then we're going to turn that into a category. And the spoiler is that we're going to see that the laws we have to the monad are exactly what we need to really turn this into a category. So we really get the category laws from the monad laws. Right? And then I think that's one way you can see that you have a sensible notion of monads, because if you change any of the laws, then you don't get the category anymore. And the category is one of these basic structures in all of this business, right? Okay, so let's just try and make this category. So we're given a monad. We ask Agda, what do I need to do to define a category? Well, I have to define what the objects are. I have to define what the homomorphisms are. I have to give an identity morphism. I have to define composition. And I have to prove associativity and the two identities that composing with the identity from the left and from the right does nothing. Right. Okay, so what should be my objects? Well, my idea was that I wanted this to be the same category as C, just that my morphisms now are these effectful morphisms, right? So I'm going to say that the objects of this new category are just going to be the objects of the original category. That's something I can say. And of course, now if I said that the morphisms here are the morphisms of the original category, then I've just made a copy of the original one. That's not very, very fun, right? So here I can say, okay, so given two objects, X and Y, which now, because the way I define them are objects in the original category, then what should be a morphism in my new category? Well, I want it to be an effectful morphism. So I want it to be a morphism which takes an X and produces a Y, but then maybe with some effects as well. And we're thinking of this monad as incorporating the effects, right? So I want to say that this is a morphism in C from X to the action of M or Y.
Right. So I like to think of these things as strategies. A strategy to obtain a Y by interacting with the environment in some way. So it's like, maybe you need to mutate some memory or communicate over the network or whatever it happens to be to get hold of a Y. This says there's a way, if you have an X, then you have a strategy to get a Y.
So I think the good example of a monad M to keep in mind is if M is the IO monad, right?
Yes.
It's in Haskell. It's saying that, well, given an X, I can get an IO or Y, which is a Y with maybe some IO actions along the way. Right? Or another good one to keep in mind is if M is the maybe monad, which is saying that given an X, I can maybe get a Y.
Yeah.
Or I can
have a
bail out.
A flaky strategy to get a Y. Could go wrong.
Okay, so I make this definition, that's something I can do again, but now I have to make sure that I can really define an identity and the composition for these things, right? So let's see what's needed for the identity. Well, it's a little bit hard to see,
Yeah,
only
be
because
bigger.
the font is too small.
Yeah.
But we see that this should be a morphism from A to A, right, in this category, which we have defined to be a morphism from A to the action of M of A. So something from A to M of A.
Yeah. So if I already have an A, then I have a very straightforward plan to obtain an A, namely do nothing and use the A I already have.
So that's exactly what the return of the monad is doing, right? So say return of M. Okay, and then here I should say A. Okay, let's bring A into scope. Return A is exactly that. So we have a way of purely producing an M of A given an A. Right. Okay. Sorry? So the return function was it's the natural transformation from the identity to M. So it goes from X to M of X. Right? So it has exactly the type we need for the identity. It also makes, if you think of this doing nothing effectful and just giving back this pure thing, then it also works quite well as what we think of the identity, right? But you shouldn't really launch any missiles when you run the identity function. Okay, what about composition? So here we're given f and g. That's the type. So f goes from A to M of B, and G.
We've got awkward C's.
Yeah, okay. Let me bring C
maybe,
into scope as well. I'll just bring A, B, C into scope. I shouldn't call it C. Okay. So right, I need to bring C1 into scope. I'm just going to call that Z. A is X.
Better.
Right. So f goes from X to M of Y. G goes from Y to M of Z. And overall, we want to compose this so we can go from X to M of Z, right?
Yeah. So given X, we have a plan to get a Y. And once we have a Y, there's a plan to get a Z. Can we put these plans together?
So, okay, so what can we do? Well, we already have something that starts in the right place, right? So I can start by doing F. Composing in C, I suppose. Okay, so F will take me to M of Y. And now I still have to get to M of Z. Okay, so can I get out of M of Y in any way? Well, I have the G, which is getting me out of Y. So if I apply, sorry, I should really fully normalize this. Otherwise, it's hard to see what's going on. So G is getting me out of Y to M of Z. So if I map M over G, it's going to go from M of Y to M of Z. That's getting me out of where I currently am, at least, right? Okay, and then I want to compose this again.
That's some progress, but we're off by one.
Composition in C.
Yeah. But now we have two M layers when we would rather have one.
Yeah, but thankfully we have a way of turning two M layers into one.
Yes.
I do.
So a plan to get a Z is straight can be turned into a plan to get a Z simply by saying, well, we do the first part of the plan and that gets us the second part of the plan.
So we see here we're using the fact that M is a monad, and we're using the fact that we can merge layers into one, right? So now we have already used most of the data that we assumed by saying that we have a monad. So we used the return, we used the join, and we used the F map, right? Okay. Right, and then if you want, you might remember last time that we defined this bind to be exactly F map of M composed with a join. So this thing here is actually the bind of G, right? Maybe it's clearer to just keep it fully expanded. Okay, so now we have to prove the laws. And associativity is always the hardest, so let's keep that one for last. And then we can see what do we have to prove here. So we need to prove that if we plug in the identity for F and then compose that with G, which is called F here, which is a bit confusing, then we get that second thing back, right? So the identity composed with G should be G. And the identity we define to be return, and composition we define to be this three-way composition in the original category. So let's see if we can make sense of this. First of all, let's bring this F into scope. I'm going to call it G so I don't confuse myself. Okay, and then we can say again something equals something 2D. Okay,
Right.
that's this. Right, it's kind of terrible. Maybe I'll write it by hand. So it's the composition in C of return and something. Right, what's this? Okay, and here I just wanted it to be G, I think. Yeah. Okay. Right, this is not completely easy. Let's actually start with the easy one, which is this one. So here I have the composition on the other side. Right, so now we have an F on the left, and then we have plugged in the return here as our G.
And
So let's see if we can make sense of this one. CF. It's just an F. Do we say that this was CF?
yes, you need to
Right,
expand id Kleisli m
yes.
to
Take a step back,
return m something.
fully normalize that. Which again looks kind of terrible. So it's F map of return composed with a join of M. Okay. Right. So what can we do in this situation? Well, we can try to remember the laws that we had,
That's
right?
important. We can also see that since there's an F here as the first component in a composition, we really, really want this to be the identity.
Yeah, because that would be great, right? If this was the identity, then we are composing F with the identity, which should just be F. So we could hope that we can just go from here to identity in C. Because if we can do that, then we have the identity law in C for F. Which says that we can cancel out this composite, right? Okay. And here now we kind of have the same F in the beginning, so we can do a conc CF something. And then what we really want is that this thing is the identity, right? But we know things about return and join. So in particular, so this is an F map of a return before a join. And actually, F map of a return before a join was one of the laws that said that this was the identity, right? So.
So that's basically saying if you take a plan and you extend it by doing nothing afterwards, it's the same as your original plan.
Yeah. So that's in some sense where the map return join law is coming from. It's that we want an identity right in this category, and we get it exactly by having this map return join. Okay, so then here we could hope that we could use one of the other laws, right? So this one talked about an F map of a return before a join, and you could hope that it would be this one, which talks about the return before a join. But what we see here is that we have a return and then we have a join, but then we also have an F map of G in the middle, right? So that law does not immediately apply. So we somehow need to shuffle things around so that this join could get here with a return, and then they would fuse together and disappear into an identity, and then you'd hope that somehow the shuffling around would have turned this F map of G into a G as well, right? But how can we do this shuffling around? Well, another thing we haven't used yet is that these return and join, they're not just a single morphism for every x, right? They're actually playing nicely with F map. They are natural.
Yes.
So
we can always bubble F map through return or through join.
yeah. So if you look at return, for example, it was a natural transformation from the identity to M. And so it's a transformation. That's the thing we've been using. But it says that if you have an F map before we transform, that's the same as having a transform before an F map. So in this case here, we have a return before an F map. So you could hope to shuffle this the other way around.
Yeah.
And then we would have the return next to the join, right?
Yes. You could do it either way, because you could use naturality of join to get you don't have two F maps
yeah,
there,
so I think
you
can't. So I think maybe
you don't get to win at that.
maybe
Yeah,
at this
the
point,
way that works is naturality of return.
yeah, so it's actually good to see what we have here. So we have return goes from x to m of x. Big enough. And naturality says that now if I do an F map after this, we do m of f, which takes me to an m of y, then that's the same as first doing the identity functor applied to f. That's just f, which takes me to y, and then return. Right. So that's what we are hoping to use here, that we have a return followed by an F map. That should just be F followed by return. So that's going to shuffle things around, and it's going to turn that F map of G into just G as well, which is good. Right. Whereas for join, it says if I have MX, and I go to MX, and then I do M of F to M of Y, that's the same as doing MMF.
Yeah. The only thing that's slightly skew with is that there should be an extra M there and an extra M there. Because that's the Kleisli arrow.
Right, right. So this is all in the original category,
Yeah.
right? Yeah,
Yes.
yeah. So I'm
Yeah,
drawing
that's
these.
what naturality says. But in our particular case, the Y's are M of something.
Yeah. Right. Okay, and then so the plan is to take this return before an F map and turn it into an F map for an return, right? But the thing that's a bit annoying now is that the bracketing here of the composition is the wrong way around. Right?
Fix it upstairs.
I could fix it upstairs, but it's just always going to be annoying.
Yes.
So it would be nice if we could automate away this annoyance. So this is the second idea that I want to talk about today. So we'll just make a little interlude. Right, I think I forgot to remove this again. Because there is something very automatic about how we deal with these rebracketing and things, right? We can always do the same thing by basically always shuffle all the brackets to the left, and then if we have any identities, we just remove them. If we have a functor applied to a composition, we can always just push that through and turn that into a composition of the functor applied to things. If we have a functor applied to identity, we can remove that as well. So we could hope to really automate this idea, right? And the way to make this work is to turn the equations that we want into equations between syntax of things. So we reify the things we want into syntactic things, and then we can work on the syntax and show that this is preserved in the semantics. So I just wanted to give a little example about how you do this. So Connor wrote a solver for this a few years ago. And the idea behind the solver is that we turn things into syntax, and then the solver can do the reshuffling, and in the end we get the equation we want. So as an interlude and example, I thought we could prove that if I have this diagram commuting, meaning that this way around is the same as that way around, and if I also have another square commuting where I share the same g, then the outer square here commutes, right? So I can paste two squares next to each other. And if I wanted to prove this by hand, I would have to do a lot of reshuffling of brackets. But I want to show how the solver does this for me now. So here's the statement. I have a bunch of objects. They are these x, y, y prime, and so on. I have the morphism, so f goes from x to y, f prime goes from y to y prime, and so on. I'm assuming that this is the same as that. My first assumption, the left square. And I'm assuming that the right square commutes. So that's saying that f prime before g prime is the same as g before k prime. And now I would like to show that all of this outer thing is the same as all of this outer thing. Okay. So the way I do this with the solver is, again, looking like equational reasoning, but a little bit more syntactic. So I start by saying, in which category do I want this? It's in category C in this case. And then rather than just a begin, I have this model begin. And then rather than just these square brackets, I have semantic brackets. So these are called semantic brackets or Scott brackets. They are often used to turn syntax into semantics.
Yes. You should think of these double struck square brackets as signifying meaning of.
Right. And then rather than just a QED at the end, I again have that in square brackets. Okay. And then here, when we have equational reasoning, I just put the left-hand side of my equation. Now I'm going to do the same thing. So this is my left-hand side. But I'm going to turn it all into syntax. So I have a syntactic version of composition called compsyn. So I turn all comps into compsyns. And I have a way of embedding real morphisms into syntactic morphisms with these brackets. So anything that's not special, I'll just embed with these brackets. And the way this works is that this is going to turn this back into meaning by just replacing compsyn with comp again and so on. Right? So then I really get an equation between this left-hand side and something else. And I'll do
Yes. So the trick is that we define a little programming language. I mean, a data type which represents a syntax for building stuff out of compositions. And then we write a little interpreter for that programming language, which interprets syntactic composition as composition and quotitons as themselves, as the actual. So the interpreter on angle brackets F gives back F. Goodness me. You can see these angle brackets are honest to goodness less than and greater than. This is the only part of this program that's still mine.
Yeah. Okay, so then when I use this solver in general now, I want to just forget about brackets and things like this. So I'm going to copy this line and turn it into a basically unbracketed line. So the first thing I'm going to do is I'm going to replace these things with an infix version. So this is a backslash semicolon, and I think it's the sixth one that looks like a semicolon. Sin, and then I'm returning, placing this, same thing. So if we look at the definition of this, it's just defined to be compsin, so that has done nothing. But now I'll remove all the brackets. So if this was not syntactic but semantic, then refl would not work here anymore, right? Because I don't know exactly how the brackets are put back in here. But the point is that the solver is going to reshuffle things for us. So in this place, I can just say solve cat refl. And it's happy with this step. Right? And I can do the same thing here from bottom to top. Right? Remove all of these and replace them with the unbracketed version. Because now here in the middle, I don't have to worry about the brackets anymore. I just know that I have these morphisms in this order. Right? And I need to make them somehow the same. Okay, and now I can start thinking, okay, what makes this the same as this? Well, I have an assumption that f prime before g prime, that's what I basically have here, right, is something else. So I could say, okay, I want to replace this with this thing. So I'll put in a focus here, saying I want to focus on this part of the equation. And when it comes into turning things back into semantics, we just ignore the focus. But the point now is that I can copy this line. Then I change the focus to be something else. So here I had f prime, g prime. And the assumption I have talks about g and k prime instead. So now, if I want to go from here to here, I can say, okay, let's reduce the problem to the smallest possible thing I have to do. So that's the reduced combinator. And then it will look at all of the pieces of making things equal here. And in this case, there's two pieces. It's making f equal to f, and it's making this focused thing equal to this focused thing. Right? So one of these is going to be hard. So that's this one that talks about the focus. The other one is just easy, so it's by definition RD. It's another combinator. Here we actually have some quality proof. So now we can move back to the semantics, and we see that if we can prove the semantic equation, then we get the syntactic equation here. And that's the one we had as an assumption. So we focus on making this into that, and then we use these combinators to supply the right proof. Right. Okay. So that made some progress. Now we have a k prime at the end. But now we would like to refocus. on this FG, because we have an assumption about F and G as well, right? So just move the focus. Okay, and the proof for moving the focus is very simple. The solver can do that. And then here now, well, I guess I can even just put the focus on this line. Because I just want to replace FG by HK, right? Which is exactly what I have. So that's by definition. This one actually has something in it. It's my F square. So you see the way you use the solver is you turn semantics into syntax, and then you have these kind of interleaving steps of moving the focus or removing the brackets. Then you actually prove something that something in the focus is equal to something else with one of these reduce steps. Then you remove the focus to somewhere else. You use the actual information you have to turn the thing in focus here into the thing in focus here, and then you continue, right? So
some of you may remember in the dim and distant past a CS 106 exercise about De Morgan's laws, which was conducted on the basis of moving a focus, rewriting by a fact, moving the focus somewhere else, rewriting by another fact. It turns out the same shit, different day. Yeah.
So if you're interested, you can look at the definition of the solver.
Yes. So the solver works by saying that we've got a way of choosing a way of normalizing these lumps of syntax. So there was we have some prejudices about which way we would like compositions to be nested and maps to be pushed through compositions. So we take a lump of syntax and we put it into its kind of standardized form. And the key fact is that the meaning of the expression before we standardize it, before we normalize it, is the same as the meaning afterwards. So this process of standardization does not in any way change the meaning of the lump of syntax. And that gives us that if we have any two expressions with the same normal form, then the meanings of the expressions are equal, because the meanings of the expressions are the same as the meanings of their normal forms, and their normal forms match on the nose. That's what the REFL is in solvcat REFL, is that the normal forms are exactly the same.
Okay, but now let's see if we can deploy the solver here to prove the identity law. So I'm going to turn this equational reasoning we had into something using the solver. So we are reasoning in the category C. Right, and then we have this kind of models begin. I'm turning these into semantic brackets, turning this into semantic QED, turning comp into comp syn. Return is not a special feature of the syntax, I just have to embed it. This is a comp syn. Fmap is a special feature, so it's an fmap syn. Then here I have to specify I want the underlying functor of M. This is applied to G, which I just have to embed. The join I just have to embed as well. Okay, and this G.
And you presumably no longer need the where open.
Right, so I don't need this anymore, indeed. Okay, so I just turned the semantic into syntax by putting syn in some places. Then the first thing I'm going to do is I'm going to turn this into unbiased, non-bracketed version by turning the composients into infix things. Okay, I think I need these brackets. Okay, that's a step I get for free. Okay, but now we said before that we wanted to use the naturality of return here, right? So I'm going to put in a focus around that. Okay, and flip it round. Well, that means that we get fmap on this side, and the return on this side. But it's not m anymore, it's the identity functor. So actually, that's just, well, I guess if I wanted to, I could say id functor c here. No, c is implicit. Okay, so to go from here to here, let's see, what do I need to prove? Well, it's the easy part. And then here, right, I just say RQ, and then I look, and then we see that this looks exactly like the naturality that we wanted to apply, right? A return before an fmap is the same as a return. Sorry, a G. So natural T. G. Right, I think, is it the same of this?
Yeah. So what's going on is that these funny focus brackets, they are added to the syntax of our expression language. And as far as the interpreter is concerned, they don't mean anything. They make no difference whatsoever. But as far as this reduced operator is concerned, that's a piece of syntax that the reduced operator can find. And that's determining how reduced computes the simplified version of Go. So it's just a little bit of extra marker that's detected.
Okay, so now let's move the focus, because what we wanted to do was we wanted to fuse this return and join together, right? And as we do it, we might as well notice that the identity functor applied to G is just going to be G here. That should all come for free. Maybe. Okay, this looks terrible. You should never look at this. That will not work. Okay, so I think the solver is not. This was not a good move to do this at this stage. I think we actually do it up here. The solver is not clever enough to see that these are the same, because they're not the same as syntax, right?
Yes.
So actually here, let's do that. Because here we're looking at the semantics. So if I put it all inside the semantic brackets, then they are the same. Okay. And then what we wanted was to say that this is a return join, so that's the same as the identity. And then the solver can get rid of that composed with identity for us. And this was another one of those we had. Which was the return join law. Right. Okay, so by using the solver, we don't have to worry about rebracketing things, and we don't have to worry about composing with the identity. But we see that the thing that actually makes this step work is the naturality of return and this return join law we had. Right. And since we have 1 minute left, and I knew this would happen, I've actually
Here's one you prepared earlier.
prepared the associativity at the bottom of the file, because this one is a bit messier.
You need to make some things appear.
Right, so you have to use a lot more naturality. Where can we see that? See that we need naturality of join, and then somewhere in the middle you have this join law as well. Right? So now we have really used all of the pieces that we needed in the definition of a monad. That
Yes.
join and return are natural, all of the laws, and all of the data, the fact that we had a return and a join and an fmap.
Yes.
So we see that in order to get the category out of these things, you need exactly the pieces we put into the monad. So that's one explanation for why we have the laws that we do.
Yes, so the proof plan here is basically to use naturality to get the F-maps out of the way, so that the joins are next to each other, and then we can use joins.
So the idea is the same. You get told this is the expression you need to make equal to this expression, and then you say, okay, I know that I can make the joins go the other way with the join, but I need to make them actually live next to each other. So I try to use the naturality to get it to work. Right. It's just a little bit more intimidating when you look at it. Okay, I think we should probably stop at this point. And tomorrow, of course, we will talk about things that are related to the coursework.